Welcome back to Calculus 2 practice problems, and today we are finally focusing on work. Work is my favorite section of Calculus 2, and you'll see why. So for work, we have a few rules. For a constant force, work is just force times distance, right? But if we do not have a constant force, we will have to integrate that force over that distance between xi and xf. We also have a special Hooke's law, which says that the force of a spring is proportional by some constant of proportionality k to the displacement of that spring. And we're going to be looking at three problems where, in order to find the work done, for example, pumping the water out of this rectangular box, right, we're going to find the work done by just pumping one thin slice or one thin rectangle of this water out of the box, right? So we're going to find this delta work. And we start from the bottom by finding first the volume of that slice and multiplying by density to get to the force. And we know that force times distance equals delta work. Then we are going to sum up all of those work slices and also take the limit as they get infinitely small. And what that just turns to is an integral over the region of that delta work, or d work, which just becomes work, right? So we're going to be using this strategy right here several times through this video. Start with delta v, multiply by density to get delta f, multiply by distance to get delta work. But before we move on to some questions, let's look at two other things. First of all, units. The units of work are intuitive because we know that work is force times distance. If we are in the metric system, force is measured in newtons, distance is measured in meters, so work is going to be Newton meters or joules. We typically call it joules because we reserve Newton meters for torque in physics, because we cannot measure torque in joules. So we typically call work joules, but if we are in the customary United States system, obviously force is pounds, right? The force that gravity has on you is pounds, or your weight, right? Also, we obviously know that distance in the customary system is feet. So we are going to call the work unit distance time, or feet times pounds, or foot pounds, right? And also, sometimes we use inch pounds if we are using a force of inches instead of pounds. Also, many Calculus 2 courses will require you to know that the density of water, if you're in the metric system, it's going to be 9,800, and the unit is newtons per meters cubed, or 62.4 pounds per cubic foot. Here's why: because we know that force is density times volume. And since volume has a cubic unit, right, it only makes sense that density has that force unit over the cubic unit, so that those cubic units will cancel and you're just left with the newtons for force. So I really don't usually go into the units in all of the previous videos, but I feel like this is the one section where units actually matter. You will probably get graded incorrectly if you say that, for example, the work was 10 newtons or 10 pounds, right? Because it is in joules. Okay, so let's look at a question. Say a force of 250 newtons stretches a spring 30 centimeters. How much work is done in stretching a spring from 20 to 50 centimeters? So my first thought process here is that work is equal to the integral of f of x dx, right? And we're going from xi to xf. So in this case, we're going from 20 centimeters to 50 centimeters. But I'm keeping in mind the fact that we want Newton meters in order to get joules, right? We could, if we leave everything in centimeters, right, we could integrate from 20 centimeters to 50 centimeters, but then our answer is going to be in Newton centimeters, right? Because the Newton is going to come from the force, but that dx, that distance measurement, is in centimeters, right? But I would prefer our answer to be in joules. So before we move on, I want to convert. Instead of 30 meters, I want to call that 0.3 meters. And instead of 20 centimeters, I want to call that 0.2 meters and 0.5 meters. That way, we're in the metric system for joules. So that means we'll be integrating from 0.2 meters to 0.5 meters. What is f of x? Well, we have Hooke's law. Hooke's law says that the force done by a spring is kx. So we do this a lot in physics, but it shows up a little bit in calculus. So let's call it kx dx, right? What is k though? How are we going to figure out what k is? Well, notice this piece of information. They told us that this force stretches it this distance. Well, F equals kx, right? And if we know that 250 newtons of force stretches it 0.3 meters, then it seems like we can solve for k. K is just 250 over 0.3. And what are the units of k? I do this because this dimensional analysis is important for this unit. Well, 250 was that measure of force, and 0.3 was that measure of meters. So our answer is going to be, looks like it comes out to 833.3 newtons per meter. That would be the units for k. Right, so we're going to use this for k. And let's see. That would mean that work is the integral from 0.2 to 0.5 of k, 833.3, repeating actually, times x dx. So we can do this integral, we can pull that 833.3, which I'm just going to write that as a fraction. If we kept it as a fraction, it would have just been 2500 over 3, right? Integral 0.2, well, let's just evaluate the integral. The integral of x is 1/2 x squared. We are evaluating that integral at 0.5 and 0.2. So I'm just going to plug all of this into an integral capable calculator to get that this integral turns into 87.5. And since we changed it to meters, now we can represent our answer in joules. If we had left it in centimeters, we would have to call it Newton centimeters instead of joules. Okay, so that's how we do these kind of spring problems. We have to recap, we're going to find k using the initial condition that they gave us, and then we're going to integrate that kx dx. This is typical with finding spring force, or the work done by a spring. Okay, so now let's move on to another kind of example. A 20-foot chain weighs 3 pounds per foot, hanging from a winch 20 feet above the ground level. Find the work it takes to wind up the entire chain. So the hard part about this problem, again, this is obviously not a constant force, right? Because the weight of this chain changes. For example, imagine you were laying halfway over this edge and half of your body was hanging. Only half of your weight, if you were distributed uniformly, only half of your weight would be hanging. It's not like as you go up, the force of gravity pulling on you stays the same. So the work, what are we integrating from and to? Well, it tells us we're winding up the entire chain. That tells me that we are going from 0 to 20 feet. But we have to set an axis. So I'm calling this right here my positive x direction. Because as we pull the chain in this positive direction, the chain is lifted up that same amount, right? So as we pull all 20 in this positive x direction, then the chain is going to be lifted up 20 feet, right? So using that as our x direction, what is f of x. That's the tricky part of this problem. So f of x is kind of like a weight. So let's think of the weight of this chain. It's going to be 3 pounds per foot, right? And we know that what could we represent like how much of this chain is left as we start pulling it up some distance x? How can we represent that amount of chain? Well, we know that this entire distance is 20, and this distance we said was x. So the difference between them, this distance right here, and by that distance I mean how much of the chain has not been lifted up, it's going to be the difference between 20 and x, right? Because if we take this little x away from all of this 20, we're going to get that distance that is left, right? But let's test this. What happens when x is 0? When x is 0, right, that would mean that this is 0, which means that we have 3 times 20, which means that the overhanging force, or weight, is 60 pounds. Does that make sense? That if the entire chain is overhanging, then we have a 60-pound force, right? Because pound is the unit on force. What if we roll the entire chain up? So in that case, the entire chain is laying on the top here. Then obviously we have no force because there's no overhanging chain. And when the entire chain is rolled up, x becomes 20. So we have 3 times 20 minus 20, which equals 0. So this function for force seems like it works for me. So that means we're integrating 3 times 20 minus x. Okay, so work, we can pull out the 3. We're going to integrate 0 to 20 of 20 minus x dx. That's going to become 3. When you integrate 20 with respect to x, you get 20x. When you integrate x, you get 1/2 x squared. We're going to evaluate that between 20 and 0. Finally, work is 3. When you plug in that 20, you're going to get 400. And then minus 1/2 of 20 squared, which is 400. So 400 minus half of 400 is 200, and 3 times 200 is 600. What are the units? Well, obviously we are in the customary system, where the units on work are foot-pounds, right? So it would take 600 foot-pounds of work to wind up this chain. Okay, so these are the two maybe entry-level work problems, either going to be a spring or some kind of overhanging chain, right? But then the best kind of work problems, in my opinion, are these word problems. Say a giant ice cream cone is filled from the bottom. It has a diameter of 4 meters and a height of 2 meters. Assume that ice cream has a density 10,000 newtons per cubic meter. What is the work required to fill this cone from the bottom? So we're filling this cone with ice cream from the bottom, and I just manually put these on some axes that will allow us to solve the problem. Well, if we were to put this on axes, if the diameter is 4, then half of the diameter, the radius, must be 2. And its height is 2, right? So this is the scale. Now, remember, this will be general strategy that we're doing. We're starting with the delta volume, meaning the volume of one slice. We're going to multiply by the density of that slice to get that slice's weight, right? It's delta force. And we can take that delta force and multiply by the distance that that slice has to travel to get the amount of work it takes to move that slice. And then once we get that delta work, we will integrate it from the bounds based on our graph, that is. So you can see that one slice of this, so we're going back to the slices that we used at the beginning of this integration applications, right? So one slice, you can see, is a thin disk, right? And that thin disk has some height, delta y, since we're on the y-axis with it. So this should be a delta y. And it's really like a cylinder, right? So the delta volume of this cylinder would be pi r squared times that height. So this is the volume of one of these slices. That delta volume is pi r squared delta y. But we need a function for that radius. We need that function to be some radius of y. So as you can see, when we're at this y value, y equals 2, our radius is 2, right? And when we're at this value, y equals 0, we're at, or our slices have a radius of 0 right there. So how are they related? Well, they're related by this red line, this red function, right? And we can see that it's growing up 1 over 1, so it has a slope of 1. In other words, it's just a line y equals x, right? And we want r to be a function of y since we have a delta y slice, right? When we end up integrating, that delta y is going to become a dy. So we want our r to be a function of y, which means it should be x equals y, right? So does this make sense? At y equals 2, we have a radius of 2. That would make sense. Pretend like this this x here is our r. So r equals 2 when y equals 2. Check. R equals 0 when y equals 0. Check. So this is a good radius function. Okay, so our delta volume is pi y squared delta y. We just proved that was true. Now how can we get the weight of one of these slices? By multiplying by density. So it's going to be pi y squared delta y times density. We had said that the density was 10,000 newtons per cubic meter in this case. Now, what is the distance that any arbitrary slice has to travel? Well, obviously the first one in, right, filling it from the bottom, has to travel 2 meters, the height of the cone. But like maybe one that's coming in halfway only has to travel half that distance. So how can we figure out how far the slices have to travel? Well, it's just the displacement, so we're back to displacement, between the top of the cone and wherever that slice is, whatever y value that slice is. So I'm going to throw this out, and then we can use it in the next examples, that the distance that that slice has to travel is going to be 2 minus y. Here's why. When y equals 0, right here, what is 2 minus 0? 2, because those slices have to travel 2, right? What about, say this slice right here is at y equals 1. How far does it have to travel to get to the top of the cone? Well, that slice in particular has to travel 1 more meter. Is that represented by our distance function? I think so, because when we have 2 minus the position that it's at, 1, we're just going to get 1. So we know this is a good distance function, 2 minus y. And we'll get more practice with this. So to get our delta work, it is our delta V times our density. So all of this is our delta F times the distance that those slices have to travel, right? So this is our delta work. And what do we do with delta work? Well, all of this stuff gets thrown into the integral, right? The pi and the y squared and the 10,000 and our distance function 2 minus y. And then this delta y just turns to a dy. And more importantly, what are the bounds of our integral? Well, where do the slices move from and to? They start here at y equals 0, and they move all the way up to here at y equals 2. Those slices are coming from 0 to 2. Okay, so now this is the most important part of doing work, is being able to set up this integral. It is not necessarily important to be able to solve the integral. Your professors will care a lot more that you're able to set it up. So at this point, you should be able to just plug it into an integral calculator. But we'll just do this one by hand. It won't be too bad. We have a 2y squared minus a y cubed. So the total work done is 10,000 pi. When you integrate 2y squared, you're going to get 2/3 y cubed. When you integrate y to the third power, you're going to get 1/4 y to the 4 evaluating that at 2 and 0, we're going to get 10,000 pi. Plug in 2, you're going to get 16 thirds minus, let's see, 2 to the 4th power is 16 divided by 4 is 4. Okay, so 16 thirds. 4 is the same thing as 12 thirds. So 16 thirds minus 12 thirds. All of this in the box just turn 16 thirds minus 12 thirds is 4 thirds. So finally, we have 40,000 over 3 times pi. And that is a unit of joules, right? Because we are in the metric system of meters. So obviously this is a big number. And that just means it's going to take a lot of work to fill up this giant ice cream cone, right? That would make sense. So let's recap the strategy. We found the amount of work it takes to take one slice of this substance up to fill up, right? One slice of this ice cream at this density took this much work, right? And we integrated that delta work slice, right? This is all that delta work. And we integrated those slices from 0 to 2. So we should be getting pretty used to that strategy of using slices and then integrating over that region to figure out like an entire volume or an entire amount of work. Okay, so also delta work is force times distance, but force is a weight, which is your volume times your density. So we're going to use this right here over and over and over again with these word problems. So let's look at this one now. What is the work required to empty a trapezoidal tank from the top by pumping out the water? Here's the thing. If you dump this tank over, there's no work being done. Gravity is doing all the work. There's no external force, because remember, work is force times distance. There's no external force that has to do any work if gravity is doing all of it. So if you drain this tank out of the bottom, no work is done. So from the top is a key word, keywords, right? So I went ahead and put these on some axes, right? X, Y, and in this case a Z axis. And then I also put it on XY plane. So with these units or dimensions, 1, 2, and 3 feet, we're able to put this on a plane. Now let's see. We're going to do the same strategy. And you can see what is the shape formed by the slice. So this one over here was obviously a circular disc, right? But what is the delta volume in this case? It's a rectangular prism, so it's length times width times height. And remember, height is just that delta y, right? It's a delta y. So what is the length and width of this slice? Well, whether that slice is here or here or here, it looks like they all have the same length, right? They all will have that same length of 3. It's their width that's changing. This one at the bottom only has a width of 1, but this one at the top has a width of 2. That tells me that it's going to be a function and a function of y. So delta v is going to be 3 delta y. Let's figure out what that function is. You can see it easier on the xy plane, that the slices here at y equals 3 have a width of 2, but the slices here at y equals 0 only have a width of 1. So what is the equation of this line? Well, as you can see, it's going over 1 and up 3. That tells me that this line has a slope of 3. And what is its y-intercept? Well, if we were to continue going down to the y-axis, it would just move down another 3, right? So it's going to be a 3x minus 3. But remember, we have a delta y, which means we want this to be a function of y. So that just means we have to solve this function for x so that it is in terms of y. We can add 3 to both sides and divide by 3. X equals y plus 3 over 3. Right? So y plus 3 over 3. Well, that works out good. The length cancels that part of the width. And how do you get from delta v to delta f? You multiply by density. So this is we do this a lot, right? That density, it said it was water, So the question now is, are we in the metric or customary system? Well, we can see that we're in the customary system because we have feet. And earlier we said that the units for the density of water, or not units, but the density of water is 62.4 in the customary system. So they may or may not ask you to memorize that number. But let's see, the density is 62.4. So the delta force, in other words, the weight of one slice is 62.4. That is the delta F. Okay, and how do you get delta force from delta work? Right? Or, I'm sorry, how do you get to delta work from delta force? You just multiply by the distance. So what is the distance that one of these arbitrary slices has to travel? Well, we can see that these ones at the bottom here have to travel a height of 3 meters, right? I don't know if I ever labeled that one on the, yeah, this was 3 feet as well. You can see it from here, right? So all of these slices, if we're using the same strategy as last time, they all will be at 3, and the distance they have to travel is that 3 minus whatever y value you're at, or they are at. So the distance they have to travel is just the displacement between them and the top of the tank. The displacement between them and the top of the tank is given by that, which, just like last time, is that 3 minus y. So we're going to be seeing this like number minus y a lot. This makes sense because at y equals 0, if y is equal to 0, they have to travel 3. That makes sense. Right? We already said that the slices at the bottom have to travel 3. And if y is equal to 3, that means these slices are already at the top of the tank. The distance they have to travel is 0. And this is taken care of in the actual integral. So the delta work is that delta force times the distance any slice has to travel, which we just said was not 6, that was last problem, 3 minus y, right? Okay, so finally, to get work, we're just going to integrate. Where do those slices have to move from in 2? 0 to 3. So do you see how this 0 and this 3 play with this distance? Because the slices, for example, at 1 will only have to move 2. Okay, so work is going to be the integral from 0 to 3. We can pull out that density, that constant density. That leaves us with a y plus 3 and a 3 minus y dy. So at this point, you could just solve this with your integral capable calculator, but I'll just do it by hand again. 62.4. Well, let's see. We're integrating from 0 to 3, and let's distribute this function. We have let's FOIL it out. We have a 3y, that is a first. Outer, we have a negative y squared. Inner, we have a 9. And last, we have a negative 3y, right? So the 3y and the negative 3y cancel each other. We're left with just 9 minus y squared dy. So work is going to be 62.4. When you integrate negative y squared, you get negative 1/3 y cubed. When you integrate 9, you get 9y. Okay, we're evaluating that at 3 and 0. 62.4 times, let's see, 3 cubed is 27, divided by 3 is just 9, plus 27. So it looks like it's just going to be 62.4 times 27 minus 9, which is 18. I'm just going to plug that into a calculator, and I get that it's 1123.2. What are the units? We are in the customary system where the units on work are foot-pounds, right? So that is how we find the work of pumping out this water out of the top of this tank, right? First. Okay. So it's really not too bad. Let's look at one final example. What is the work required to pump gasoline out of a cylindrical tank 5 meters underground up to the pump. Assume the tank has a length of 5 meters and a diameter of 2 meters. Assume that the density of gasoline is that of water. Okay, so if this tank, because of the way I positioned it on my axes, all of the slices, like these blue slices in this cylindrical tank, have to move. Let's see. If this tank has a diameter of 2, then this is a y value of 1, 2, 3, 4, 5, 6. All these slices have to move all the way up to 6, right? Because if it's 5 meters underground, that means that, so like if this is the ground, the tank is 5 meters underground. So the slices at the bottom have to actually move 7, right? Because the tank has a diameter of 2. So that'll all get taken care of in the integral. So let's see. Once again, our delta volume is a rectangular prism, right? Even though it's a cylindrical tank, a cross section of a cylinder would leave you with a rectangle. So it's length times width times that height, delta y, right? So once again, the length is not changing. Whether those slices are at the top or the middle or the bottom of the tank, they all have that length of 5, right? It's their width that's changing. When they're at the top or bottom of the tank, right, here or here, those slices have a width of 0. But if they're in the middle of the tank, for example, the width of that slice is going to be that diameter 2. So how can we represent that function in terms of y? Well, this is a circle, right? X squared plus y squared equals r squared. R squared is not 4. Since the diameter is 2, r is 1, so r squared is 1. So we want this to be a function of y, right? So let's just solve this for x. X equals plus or minus the square root of 4 minus y squared. We have to do a plus or minus. Here's why. This half of the semicircle, right, this half of the semicircle is represented by the positive square root. But here, where we're at the negative y values for this half of the semicircle, it's represented by the negative square root. So I almost want to make a note of that, that this half of the semicircle is x equals negative square root of 1 minus y squared. And this half of the semicircle is x equals positive, not 4, 1 minus y squared. I wrote 4 again. 1 minus y squared. Right, this will be important when we're talking about displacement. So what is the width of the slice? It is the displacement between this function and this function. So the width is the displacement between 1 minus y squared and negative 1 minus y squared, right? These two negatives will make a positive, and we just have the square root of 1 minus y squared plus the square root of 1 minus y squared. So it's really 2 square roots of 1 minus y squared. This is because it's symmetrical. For example, we can find this width right here and double it to find the entire width, right? But you have to keep track of this negative right here if you don't do that symmetric approach. So that just means that at any given y value, this would be the width of a slice. But let's check it. What happens when y equals 0? Right here on the x-axis, when y is equal to 0, we know that those slices have a width of 2, right? The diameter of this tank. So plug in y equals 0 into our width function. Let's make sure that we get 2. We get 2 times the square root of 1 minus 0, so 2 square roots of 1. It's like 2, so that's check. We also know that at the bottom of the tank, right, here at negative 1, and also at the top of the tank, here at y equals 1, the slices have a width of 0, right? The slices at the very top and bottom of the tank have a width of 0. So when we plug in plus or minus 1 into that function, we should get 0. Let's see. 2 square roots of 1 minus plus or minus 1 squared, either if it's plus or minus, we're going to get a 1. 2 times the square root of 1 minus 1 is just 0. So once again, we proved that we did our radius or width function correctly, right? So the width can be represented by 2 square roots of 1 minus y squared. Okay, let's move to delta F by multiplying by, hopefully you have it by now, density. We multiply by density, we get weight, or delta force. So we have 5 times 2. That's going to make 10 square roots of 1 minus y squared. Delta y times density. And it said treat gasoline as it has the same density as water. Since we are in the metric system here, we know that water has a density of 9,800 newtons per cubic meter. Finally, we are going to go to delta work. What is the work required to move one of these delta slices up to this y equals 6 value? We already said that based on the way that we drew, or that I put this on the axis, right? You could have done it a different way. It would just change your width function and your distance function. But the way that I set it up is that since I centered the tank here at 0, the slices have to move 5 meters above the tank. But the top of the tank in my picture happens here at y equals 1, which means that all these slices have to move to y equals 6. So the distance function, let's see, it's 10 square roots of 1 minus y squared times 9,800 times delta y times the distance that any of these slices have to travel. That's going to be 6 minus y. Let's also prove that one. So I want to change all this to a white color. All this white color is us checking our work. Let's see if 6 minus y will work. Well, when the slices are at the top of the tank, right, when y equals 1, we have 6 minus 1 equaling 5. Do the slices at the top of the tank have to move, or picture it as the gas at the top of the tank only has to move 5 meters. Is that true? Yes, it's already at the top of the tank, so it just has to move the 5 meters to ground level. Okay, what if we're half in the middle of the tank when y is equal to 0? That's just the way that we set up our axes. Do the slices of gas in the middle of the tank have to move a distance of 6? Yes, because that's the way we set it up. But how about slices at the bottom of the tank? Gas at the bottom of the tank, 6 minus, we know that from the picture we drew earlier over here, the gas at the bottom of the tank has to travel 7 meters, right? So how are we going to do that with a 6? Well, 6 minus y, but the slices at the bottom of the tank have a y value of -1. Negative 1 is a positive 1, so we have 7. So now we have proved that our distance function works perfectly, right? Now we are going to integrate. Where are these slices moving from to 2? From to 2. They're starting here at the bottom of the tank at y equals -1, and they're coming here just to the top of the tank, not all the way to 6. It's a common mistake. Where are the slices bounded? Just between the bottom of the tank at y equals -1 and the top of the tank at 1, right? So it's -1 to 1. We can pull out, well, we'll just leave it in for now, 10 times 9,800 times the square root of 1 minus y squared times 6 minus y dy. Okay, so that is how you set up this integral. And we would pretty much have to solve this integral with an integral capable calculator, because if we didn't, it would take us probably 20 minutes, and I don't think it's worth it for the time in this video. But essentially what we could do is distribute this square root to both this and set it up as two different integrals, right? This one with the y out front of it, if we have a y square root of 1 minus y squared, that one's easy, because we can just u sub the inside and we have a du out front. But for that other integral, when we distribute this square root to that 6, and we're just left with 6 square roots of 1 minus y squared, the integral of that one is pretty challenging, because what happens here is it looks like an arc sign, right? It looks like an arc sign, except it's not under 1. So what do we do when it looks like an arc sine, but it's not? We do a trig sub. We would sub for, instead of x, we could do a trig sub for y equals a sine theta. A in this case is 1 because a squared is 1. We'd set y equal to sine theta, right? And it's just not worth it to do for this video because we already did all of the trig sub videos. But setting up this integral is the key part. So that is how we do work problems. Finally, we can actually use integration for a purpose, right? That is how you do work problems.